Hi everyone, today we are going to look at the Leetcode problem path sum. And here the problem statement says that given the root of a binary tree and an integer target sum, return all root to leaf paths where the sum of the node values in the path equals target sum. Each path should be returned as a result of the node values, not node references. So a root to leaf path is a path starting from the root and ending at any leaf node. A leaf is a node with no children, like 7, 2, 13, 5, 1. These are leaf nodes. And here we have this input. We can see that 5, 4, 8, 11, null, 13, 4, 7, 2, null, null, 5 and 1. Here the null is because the 13 doesn't have any children, and here this null is because the 4 doesn't have a child. It has only one child here, and the output should be 5, 4, 11, 2 and 5, 8, 4, 2. As you can see that these are the two paths whose sum equals the target sum. So today we are going to look at this problem where we are going to find all the root to leaf paths in a binary tree where the sum of the node values along each path equals the target sum. And we have seen that the input is the root node of the binary tree here, where each node has an integer value, and left and the right child pointers, that is left or right, which may be null. And also we have a target sum, which is an integer representing the desired sum of the node values along each path. So here we have this constraint. It says the number of nodes in the tree should be in the range 0 to 5000, and node values should be, oh no, just give me a minute. Okay, I need to take that problem again. So the problem number is 113. Yeah, we can see the constraints here, and yep, so we can see the constraints. The node value should be minus 1000 to plus 1000, and the target sum can be anywhere from minus 1000 to plus 1000. And the output, it should be a list of lists where each inner list represents a root to leaf path. That is a sequence of node values whose sum equals the target sum, like like here you can see 5, 4, 11 and 2. So this becomes a list, and another list would be 5, 8, 4 and 5. Okay, so now how are we going to solve this? We can solve this, and also before trying to solve this, I would like to define some edge cases. So there are few edge cases we can think about, like empty tree where the root is equal to null, and that would return an empty list. And what if there's a single node, root is equal to value, so that just only one value, like root is equal to just one, like in the list, and that would return a list which contains only the given value. If the value is equal to the target sum, else it would return a empty list again. And what if there are no valid paths? Tree has path, but none sum to target sum, none equals to the target sum, so again we are returning the empty list there. And what if we have negative values? Node values can be negative, so we can't prune paths based on sum exceeding the target sum. So what if it's a large tree up to 5,000 nodes? So we need to, efficiency matters, we need to think about that. And deep tree. So what if the long path, that is a skewed tree, affect the path length and the stack usage? That is something to think about. And so here the possible solutions could be, we could use recursive DFS with backtracking, because so when we think about recursive DFS with backtracking, it's just that we would like to explore all the root to leaf paths. So, and also we can maintain a single path list to track the current path and a current sum to track the sum. And also we can use backtracking by removing the last node after exploring a subtree to reuse the path list. So here the algorithm can go something like this. So first it checks for the base case, which is like if the node is null, then return, then add the current node's value to path and update the current sum. So let me write it down here. So here, so here it's the recursive DFS, right? So I'm going to write this algorithm here. So first we are going to check the base case, which would be if node is equal to null, then return. Then we are gonna add the current node's value to path and update current sum. Like for example, if we are here, if this is the current node, then we are going to add this current node's value to the path, like 5, 4, and update the current sum. The current sum would be 5 and 4, which would be 9. And so if at a leaf node dot left is equal to null and node dot right is equal to null, and current sum is equal to target sum, then we have to add a copy of path to the result. and then we are going to recursively explore left and right children. Backtrack. Remove the current node from path after exploration. So here's a code we have. So here, just give me a minute here. So here, let me take a look at it. I'm going to run this code. Is there a change? I think there was some typo there. I don't know where the typo is. Let me just, okay, yes. Yeah, here you can see that it's returning the output that we wanted with the first example. And so here, if I have to explain this code, I would say like here we are initializing the result, and here we are initializing the result, and it's creating an empty list to store all the valid paths, and then here we are handling the empty tree. If root is equal to null, then return this empty tree, which would be as like an empty list as of now, because we just initialized it. And then we are calling the DFS helper here. So here we are saying like so this initiates the recursive DFS traversal starting at the root. So the parameters, as we can see, it's the root node, and that is for the first example, it would be the node with the value 5, and then we have target sum, we have the current sum, that is the initial current sum would be no nodes, and then like would be 0, and then like and here the target sum for the first example is 22 here, and list of integer, here we have this path, it's a list to build the current path. and then like we have an answer, which is the reference to the result list to store valid paths. And here so as you can see here, like here we are appending the current node's value to the path list. So initially it would be like 5, and then we are adding the next step, we are adding the node's value to the running sum. So let's say first it's 5, and here like the first here first it's 5 because that's the current um, that's the first node's value, the root node's value. And then this builds a path and sum incrementally as the traversal progresses. And here we are checking for leaf node and valid sum. So if node dot left is equal to null and node dot right is equal to null, and the current sum is equal to the target sum, so this is the condition that the node is a leaf with no children and the path equals to the target sum. So what does it mean? That means we need to add it as a add this path to our result, which is ans, and yeah, so so yeah. And then we are gonna recurse on children, as you can see, like DFS, node dot left, target sum, current sum, path, and ANS. So this recursively process the left subtree, passing the updated current sum and path. And then we are gonna recursively process the right subtree using the same current sum and path. So here DFS, node dot right, target sum, current sum, path, and ANS. And this follows the pre-ordered traversal order. That is, it processes the current node, then left, and then right. And then we can, here we are backtracking. So we can see that we are removing the current node's value from the path to backtrack. This allows the path list to be reused for other paths, that is exploring the right subtree after the left. So backtracking ensures the path reflects the correct state for the next recursive call or parent node. So if we want to like do an example, if you want to like do an example like do a detailed execution of the example 1, I would like to, let's see, like initially we are saying like the first call would be path sum of root and 22. So that would be the first call. And so here root is not null, and so it doesn't return the empty list. And then what else it does is it calls the DFS. So DFS with these parameters. 5, 22 is the target sum, 5 is the value of the root node, and 0, that is the 0, and because as we can see, it's 0 is hard coded there, because like currently the current sum is 0, and 0 is in the place of the current sum, which is 0 obviously initially, and then we have an empty list as we initialized, and then ans ans, which is again like an empty list as we initialized. So this is the path, current path, which has nothing in there, so it should be an empty list. And so the first call for the DFS would be, we have to just copy and paste here, so that's how it's gonna be. So then for that, as I said, like 5, and the current sum is like 5, and path, we are adding 5, so let's put 5 within a list, because we know path is a list of integers, and it's checking, it's not a leaf. Is it a leaf? No, this is not. So if it's not a leaf, then we are going to recurse here. What are we going to do here? DFS, and 4. So the node dot left, this is the node dot left, the left node to the root, and that would be 4, and the target sum is 22, and we know that the current sum is 5, and currently in the path we have only 5 there, and answer. So we are doing the we are calling this recursive DFS, and so what would be that? So again, now the node would be 5, so it's not null, and we are adding 5 to the path, because we already have 5 in the path, so we are adding 4 to the path, and then the current sum would be plus node's value, which is 4, so it's going to be 9 now. And is this a leaf? No. Is 4 a leaf? No, this is not a leaf, because node dot left is not null. Even though node dot right is null, we have node dot left, which is not null, so this is not a leaf. So what are we gonna do? So we are going to call the DFS again. So that would be DFS 11, because 11 is the node dot left, as we can see there. Node dot left is 11, and target sum is going to be 22, and current sum is 9, and path, currently we have 5 and 4 in the path, and ANS. And then let's do that. Okay, so now node is no dot value is equal to 11, and so we are going to add 11 to the path, and the current sum would be 9 plus 11. That's gonna be 20. And we are checking if it is a leaf. No, this is not a leaf. It has both no dot left and no dot right, and also the current sum is not equal to a target sum, and so what are we going to do now? We are going to call the DFS, and this time what is the no dot left? The no dot left is 7, so that would be 7, and 22, which is the target sum, and 20, which is the current sum, and the path, the list of the current path, 5, 4, and 11, and ANS. Okay. So now the no dot value is 7, so we are adding 7 to the path, and the current sum would be 20 plus 7, which is 27. And is this a leaf node? Yes, of course, because no dot left is null and no dot right is null, and is the target sum is equal to yeah, but the target sum is not equal to 22, it's 27. So what are we gonna do now? It's like, so we are not adding it to the answer. So yeah, we can only add it to the answer if the current sum is equal to the target sum, but the current sum is 27, which is not equal to the target sum, which is 22. So what are we gonna do right now? So we are going to recurse. So this time it is going to be DFS null, because the no dot left is null, and the target sum is going to be 22, and the current sum is 27, and the path consists of current path consists of 5, 4, 11, and 7, and answer. So now, so here the node is equal to null, yes, so it returns immediately. And so where do we return here? We return here, and then we have here DFS and then we call this DFS with no dot right. So what is no dot right? Again, it's null because it's a leaf node, so we are going to say null 22, 27, and 5, 4, 11, and 7, and ANS. And again, it returns immediately because the node is equal to null, so return. So it returns immediately. Right here. So now we are backtracking. So path dot remove path size -1. So the path is 5, 4, 11. Oh, okay, got it. So path size -1 would be this one. So the path is going to be, currently the path is going to be 5, 4, and 11. Now what are we going to do? We are going to so we backtrack now. So we are at 11. So now we are going here. So recurse on the right child. We are going to call the DFS with 2, 22, 20. Yeah, it's from here. 2, 22, 20, and 5, 4, 11. And again for this one, the node is 2, and we are adding 2 to the path, so we would be adding 2 right here. So the current sorry, excuse me. So the current sum would be 22, and this is a leaf node because node dot left is equal to null and node dot right is equal to null. So this is a leaf node, and the current sum is equal to the target sum. So we are adding it to the answer list of integers. So we are adding this whole list, this path list, to this ANS, and which is the answer. And let me add it here. Let me mention it here. So it's gonna be 5, 4, 11, 2. And then now we are going to recurse again. So this time it's going to be DFS null 22, 22, 5, 4, 11, and 2. And ANS. So again, because it's null, it returns and DFS null for node dot left and node dot right, comma 22, comma 22, 5, 4, 11 and 2 and ANS. So again it returns because the node is null. And now we are backtracking. Let me just paste it here. Now we are backtracking. So we have to remove the last one, which would be, so now the path would be 5, 4, 11, because we removed 2, which is the last node in the path. And so now where are we? We are right here. And then so now we need to backtrack again. So that would be so this would be the parent node right now. And now the right child, as we can see, that right child is null. So again we need to call the DFS with null, which is going to return immediately. So we are going to call DFS (22, 9 and 5, 4. Now again we need to backtrack, and now the path is going to be 5, and so here we went to the root node, and here the node dot right. So here we are going to call, now we are going to call the DFS from there. So we are going to call the node dot right of the root node. So that's going to be DFS so the node dot right is 8. so it's going to be 8, and 22 is the target sum, and 5 is in the it's a current sum, and currently we have only 5 in the path and ANS. And okay, so here again what's happening here, so here we are going to add 8 here and add 8 to the path, and 5 plus 8, that's going to be 13. And is this a leaf? No, this is not a leaf. It has no dot right and no dot left. So we are going to here DFS, we are going to recurse again with 13. No dot left is 13, right? Yes, no dot left is 13, and the target sum is 22, and the current sum is 13, and 5 comma 8, that's the current path and ANS. And now remember, we need to do the right child later, not right now. So that would be, so when we go with 13, so we are going to add 13 to the path, and 8 plus 13, it's going to be 26. And then, is this a leaf node? Yes, it is. And so no dot left is null and no dot right is null, but current sum is not equal to the target sum, so we cannot add it to the ANS list of lists. So we are going to, what are we going to do right now? So we are going to recurse again. So again, we are going to call the left and the right, they both are going to be null, and we are going to return immediately. So DFS null, comma, it's going to be really pretty quick, 22, comma 26, comma 5, the path as 5, 8 and 13, and ANS, and it returns immediately because the node is null. And then we are going to call DFS null, the node dot right, which is null again for 13 for this particular node, because it's a leaf node. 22, where is it? Yeah, sure, 22 and 26, that's the current sum, and the path, current path is 5, 8 and 13, and ANS, so it returns. So what are we gonna do now? Backtrack. So when we backtrack, the path is only going to have 5 comma 8, and then now so we are at 8 here, right here. So we are going to continue the DFS like for the 8, which is now because we already did the 13, it's going to be 4 this node right here. So what are we gonna do right now is we are gonna call on the right child, which is DFS 4 comma 22 13 comma 5 and 8 comma anus. And now the node is going to be 4, and so we are going to add it to the current path, which is going to be 4. Current path is 5 comma 8, and then add 4 to it, and then the current sum would be 17. And then, is this a leaf node? No, it is not. It has both the left and the right nodes. And so now we are recursing again. Are we here? Where are we? DFS 5 comma 22 comma 17 comma 5 8 4 and NS. And then so when we do that, what happens? So yeah, we are right there. So now we are adding 5 to the path, and what would be the current sum? It's going to be 22. Excellent. So now, is this a leaf node? Yes, this is a leaf node, because node dot left is equal to null and node dot right is null, and the current sum, yeah, so it is a leaf node. And also the other condition, current sum is equal to the target sum, so we are adding it to the list of list ANS. So ANS is going to be, let's add this one more list here. 5 comma 8 comma 4 comma 5. Okay. Then again we are going to recurse. So now we have to recurse for null and null, which is because both left and the right nodes are null, and it's going to return immediately. So it's going to be null 22 22 5 8 4 5 and NS. So this returns because the node is null, and then again we are here, the DFS is going to be now 22 22 5 8 4 5 and NS. Now we are going to backtrack. So the path is going to be 5 8 and 4. So here it's going to be, yeah, 5 8 and 4. This is where we already handled this, so we are going to handle the node dot right now, which is 1. So we are going to say DFS 1, 22, 17, 5, 8, 4, ANS. So here, yeah, again we are going to add 1 to the path, and the current sum is going to be 18. And is this a leaf node? Yes, it is, because the node dot left is null and node dot right is null, and but the current sum is not equal to the target sum, so we cannot add it to the list of list ANS. And yeah, so now we are going to backtrack, so that here now we need to backtrack, and the path is going to be 5, 8. So here we are 5, 8. We already handled 13. So we are gonna backtrack again to the parent node, which is gonna be, we're gonna backtrack again. So here we are, and we handle both left and the right nodes. We are going to backtrack again. That would be so now the path sum is going to be, we know the answer, so we are going to return it, return this ANS. And as I would like to say, I mean, if you want to visualize the traversal, this is a pre-ordered traversal. And so like if you want to explore the path, it's like the path is going to be 5, 4, 11 and 2. So this is how the DFS traverses. So basically, like DFS calls 5, 4, and this calls would be 5, 4, 11, let me make it an arrow here, and 2. So yeah, here 5, 4, 11 and 2. So yeah, the path builds up is going to be empty list 5 to the list containing 5 and 4 to the list containing 5, 4 and 11 to the list containing 5, 4, 11 and 2. So at 2 we know 2 is a leaf node and the sum is 22. We have added 2 to the answer. And if you want to backtrack, this is how the backtrack works. So the backtrack would be just the reverse of this. At first it stops there because it has to handle the right node, and so the same for the other path. The other path would be the other path that adds up to the target sum is, as we have seen, it's the other list in the ANS is 5, 8, 4 and 5, and I think yeah, it's the same thing, so I don't want to write here, or okay, I think I'll just write DFS calls 5, 8, 4, 5 and the backtrack would be just a reverse of it. So these are the key features of the solution. The pre-order traversal. The DFS follows pre-order, process current node, path add, current sum, and then processes the current node, that is like adding to the path and adding to the current sum, and then the left child and then the right child. Ensures paths are built top down from root to leaf, aligning with problem's requirements. And then we have backtracking. This is another key feature of the solution. It uses a single path list. It's modified by adding path that add and removed, and removing path dot remove node values. And after exploring a node subtrees, backtracking removes the node's value to reuse path for other paths. That is, after 5, 4, 11, 2, backtrack to 5, 4, 11 to explore 5, 4, 11 and 7. And then so this reduces the space complexity by avoiding multiple path copies. And then we have leaf checking, which is another key feature of the solution. So at each leaf we are checking if it's the node dot left is equal to null or the node dot right is equal to null. And also we are adding another condition to suit the problem statement to check if the current sum is equal to the target sum, and if true, it adds a copy of the path to the ANS to preserve the path before backtracking modifies it. And efficiency, the efficiency I would say O of n plus P dot h, where n is the number of nodes visited once, that is O of n, and then P would be the number of valid paths, and h would be the tree height or path length. And so path copying at leaves should be O of P dot h. So typically approximates to O of n if P is small. And then if we have to talk about the space complexity, I would say it's O of h. So the recursion stack up to h calls and the path list up to h elements, where h is the tree height and it excludes the output space, which is O of P dot h, which is path copying at leaves, and then balanced tree, which should be h is equal to O of log n. For skewed tree, it would be h is equal to O of n. And yeah, so that would be the end of this video, I guess, or I think that would be the end of this video. Thank you for watching.